Welcome. This is a deep dive into the migration framework in luz-docs, the campaign and executor pattern. It's how we run large, one-off data migrations across every tenant, safely, without ever touching the request path. We'll use the materialize backfill as the worked example throughout. 6 parts. First, what the framework is for and why it exists. Second, its 2 core abstractions, campaign and executor. Third, the campaign's lifecycle. Fourth, the 5-phase pipeline that actually runs it. Fifth, how it guarantees a campaign runs exactly once per tenant. And sixth, inside a real executor, the materialize backfill, its resume behavior, and how completion is detected. First, the problem. A code change can't reach data that's already written. So when we add a new field or shape, millions of existing documents per tenant have to be swept and updated, and that comes with some hard constraints, building up here on the right. The constraints are real. It must never slow a user request, it must survive a pod crash mid-run, it must run exactly once per tenant, never double processing or skipping, and it must stay gentle on the database. The answer comes in 2 parts. A campaign, the named unit of work with a persisted status and a lifecycle, and an executor, the batched worker that does the migration. It runs at night, off the request path, and resumes after any crash simply by re-querying what's left. 2 abstractions bound one-to-one. On the left, the campaign, the what. In the middle, the executor, the how. And on the right, how the campaign finds and calls its executor at runtime. A campaign has 2 faces. First, a registry entry, a constant in the campaign enum declaring its name, summary, enabled flag, per tenant include and exclude filters, and the executor it's bound to. Second, a persisted record in the migration campaign collection, 1 document per tenant, holding the subject, the status, an attempt counter, and a last updated timestamp. Notably, no cursor. The executor is just a functional interface, a result execute method taking a JWT and a tenant ID, returning a status, completed or incomplete, plus a freeform detail, like total and failed counts. It's stateless and idempotent, and owns its own batching. At runtime, the enum resolves its executor bean through CDI. Adding a migration means adding an enum constant and an executor class. Everything that schedules, locks, runs, and retries it is reused. The campaign's lifecycle is a tiny state machine. Just 3 states. Watch how it moves and how a crash is recovered. A campaign starts incomplete. When a run begins, it goes in_progress and the attempt counter ticks up. If the executor finishes cleanly, it becomes completed, a terminal state that every phase then skips. If some items failed, it returns to incomplete to be retried. And the crash case. If a pod dies mid-run, the status is left stuck at in_progress. The next nightly drain notices in_progress with no live lock, concludes the pod crashed, and resets it to incomplete for redispatch. The persisted record is deliberately minimal, subject, status, attempt, timestamp, and there is no cursor, because progress is rederived from the data on every run. Here's how a campaign actually runs. 5 phases building up left to right. A passive daytime trigger, an async schedule, a nightly cron, a single writer drain, and finally the locked execution. 2 durable queues decouple them. Phase 1. Every HTTP request fires an async event per enabled campaign, fire and forget, so the user waits for nothing. Phase 2. A read-only handler gated by a 24-hour DDAP key publishes a job to the idle queue. It never writes campaign state. Phase 3. A nightly cron calls an endpoint behind a bulkhead of 1, so only a single drain runs. Phase 4 is the single writer. It finds or creates the campaign record, checks the status and the lock, renews the tenant token, and promotes the job to the active queue. Phase 5 is execution. A push subscriber acts the message first, checks the curfew window, adds a little jitter, takes an 8-hour lock, flips the status to in_progress, runs the executor, and writes the final status. Crucially, no heavy work ever happens on a user request, daytime-only schedules. With many pods and a nightly stampede of jobs, how does a campaign still run exactly once per tenant? 3 independent guards appearing here one by one. First, the 24-hour dedup key, set in Phase 2 before publishing, collapses the daytime request storm into at most 1 scheduled job per day. Second, the single writer drain. Only the nightly drain creates records and dispatches, and a bulkhead of 1 rejects any concurrent invocation, so there's exactly 1 writer of campaign state. Third, the execution lock. Before running, a pod takes a distributed lock with an 8-hour expiry. A second pod is blocked by the lock and by the in_progress status as a backstop if the lock ever lapses. On top of that, the messages act before work begins. A 1 to 3 second jitter closes the lock race between pods, and a curfew keeps the heavy work inside the night window. Now inside a real executor. The materialize backfill. It's a simple batch loop, shown step by step, with a worked example of 1 document on the right. The loop pulls 300 documents that are missing any sentinel field. Each document runs on its own future, but a semaphore of 3 caps it to 3 in flight, a gentle burst, never a flood. For each one, it looks up the folders with a 30-minute cache, computes the state, and sets the 4 fields. The set operation backfills cleanly onto legacy documents. A failing document increments a failed counter and is added to an exclude set, so it's skipped for the rest of the run. 1 bad document never stalls the batch. The loop repeats until a batch comes back empty, then returns completed if nothing failed, otherwise incomplete. And notice the key trick. There is no cursor. The query itself is the progress marker. A stamped document never matches again, so reruns pick up exactly where work was left. That query-based progress is what makes the whole thing crash-safe and idempotent. 3 ideas here: why it's safe, the resume loop, and how completion is measured. Why it's safe. Writing the same computed fields again is harmless. So at least once delivery and overlapping retries are fine, and a crash mid-batch leaves finished documents done. The query just won't return them again. The resume loop. A crash leaves the status at in_progress. The next drain resets it to incomplete. A fresh run starts, and the query finds only the remaining documents, never restarting from 0. And completion is measured, not flipped. The materialize gate simply counts the documents still missing fields. 0 means complete, cached for about an hour. Otherwise incomplete, cached for about a minute, so it rechecks often. There is no explicit switch. When the backfill drains the last document, the next gate check reads 0, and the tenant moves to the fast path on its own. So why does this framework hold up? It's reusable. A new migration is just an enum constant and an executor class. It's off the request path, daytime-only schedules, and the work runs at night. It runs exactly once per tenant, behind 3 guards. It's crash-safe and idempotent, with no cursor to corrupt, and completion measures itself. Campaign is the what, executor is the how. In one breath. A campaign is a named, persisted, per-tenant migration. An executor is the batched worker that runs it. Daytime-only schedules. A nightly drain dispatches. A distributed lock keeps exactly 1 pod executing. Progress lives in the data, so resume is just running the query again, and completion is measured rather than flipped. Add a migration by adding an enum constant and an executor class, and the whole pipeline that schedules, locks, runs, and retries comes for free. Questions?